Okay, so far in 11.2, we've talked about continuity and the three different criteria in order for a function to be continuous. We've also talked about the two different types of discontinuity, removable discontinuity and non-removable discontinuity. Now let's take a second to look at this chart and figure out where certain functions are continuous, depending on what type of function they are. If you look at the first one, polynomial functions, that's when we have a whole bunch of different terms added or subtracted together. An example would be y equals 3x to the fourth plus 2x cubed minus 7x plus 5. We can do any sort of quadratic, any sort of linear, cubic, any sort of polynomial goes under this category. In any sort of polynomial, our functions are continuous for all x values, or all real numbers. Sometimes they're just a straight line, sometimes they're a parabola, sometimes they have a whole bunch of curves, but no matter what, there's no holes, there's no vertical asymptotes, there's no gaps, and so any polynomial function is continuous everywhere. Now, the next one is rational functions. That's when we have a polynomial in the numerator and a polynomial in the denominator. And as soon as we see that denominator, that should raise a red flag. As soon as we see that denominator, we know that that denominator can never equal 0. Now, a couple things could happen when we have a rational function. We could have a vertical asymptote, or we can have a hole. Remember, a hole is when there's a factor on the top that cancels out with a factor on the bottom. For example, in this function right here. If you were to factor the numerator, there would be a hole in this graph at x equals -1. But a hole, remember, is removable discontinuity. So this would be discontinuous at x equals -1. In this other rational expression, there isn't a hole, but there is a vertical asymptote at x equals -1, where that denominator equals 0. A vertical asymptote is non-removable discontinuity. So that rational function would have non-removable discontinuity at x equals -1. So we have to look as soon as we have that denominator to see where that denominator is going to cause us issues in our domain, whether that's a hole or a vertical asymptote. Then there's going to be discontinuity there. The next one is any sort of root, square root function, or any really even root. We know that underneath our square root can never be negative, because there is no such thing as, for example, the square root of -4. There are no numbers, the same two numbers, that multiply together to give us a negative. So we know that negatives underneath a radical are not real numbers. You might have heard of them being imaginary numbers, but they're not real numbers. So we know as soon as we see a square root that should also raise a red flag for us, that everything underneath that square root has to be greater than or equal to 0. So in this case, x plus 3 has to be greater than or equal to 0, which means x has to be greater than or equal to -3. So wherever that's not the case, my function is discontinuous. So in this problem, he would be discontinuous from -infinity to -3, or it would be continuous from -3 to +infinity. As soon as I see that square root, that should raise a red flag. The last two functions we're going to talk about are exponential functions and logarithmic functions. An exponential function is where we have our variable up in our exponent. For example, e to the x, or maybe even 4 to the x. An exponential function is going to go really close down here and have a horizontal asymptote, and then it's going to kind of shoot up to the sky like that. You notice that there are no holes, there are no vertical asymptotes. It's going to touch every x, and you can kind of follow your pencil along that function or that graph, and there are no holes or points of discontinuity. So for any exponential function, it is continuous for all real numbers. For any log function, we just need to make sure that this x is positive. So making sure that the x is positive and then it's continuous wherever x is greater than 0. Okay, so now that we've talked about that, let's look at example number 2, and let's figure out where these functions are continuous or maybe where they're discontinuous. So if you look at example number 2, the first one gives us a rational function. We have f of x is equal to 4x minus 3 over 2x minus 7. As soon as I see that denominator, I have a red flag. I know it doesn't look like a red flag, but that's my horrible drawing of a red flag. As soon as I see that denominator, I know that that denominator can never equal 0. I tried to factor the top, I tried to factor the bottom, but there was no factoring involved and there was no factor that's reducible from the top to the bottom. So I know there's not any holes. But I do know that denominator can never equal 0, or that's going to cause a vertical asymptote in my graph. So when I solved that equation, I got x equals 7/2. That means this function has a vertical asymptote at x equals 7/2. It's discontinuous at x equals 7/2. There is non-removable discontinuity there at 7/2. I would have to plug this function into my calculator to figure out what it looks like at that vertical asymptote. They're either both going to go up, they're both going to go down, or they're going to go opposite and the limit's not going to exist. Now, depending on how they ask the question, for example, on my test that I normally give in class, if we were back in class, would ask you where is this function continuous and ask you to write it in interval notation. So your answer would look something like this. This function is continuous from negative infinity to 7/2, and then again from 7/2 to positive infinity because of that vertical asymptote. Now on my math lab, they sometimes tend to ask the questions a little bit weird. And so the answer for my math lab is going to look something like this. This function is discontinuous at a single value of x equals 7/2, and the limit does not exist and is not positive or negative infinity. So on this graph, one must go up and one must go down as it hits that vertical asymptote, and so the limit doesn't exist. Now, if it hit a vertical asymptote and they both went up, then we would say that it does equal positive infinity as our limit. But this has a single value where it's discontinuous, 7/2, and the limit doesn't exist. So a little bit weird wording on the My Math Lab question, so just be careful with that. So be able to answer the questions all different ways that they give it to you. Let's look at B. B says that we have the function g of x is equal to e to the 2x minus 3. I notice on this function that my variable is up in the exponent. So I know this is an exponential function. I know that in any exponential function, we have no holes, no gaps, no vertical asymptotes. So I know that this function is continuous everywhere from negative infinity to infinity, or it's continuous for all real numbers. Last one in this video, we're going to look at C. F of x is the square root of 5x plus 3. There's my ugly red flag again. I had that red flag because I noticed that there was a square root. And I know anytime I have a square root that anything underneath that square root has to be greater than or equal to 0, has to be positive. I can solve that equation by subtracting 3 to both sides and dividing by 5. And then I know that x has to be greater than or equal to negative 5/2. If it's not greater than or equal to negative 5/2, then there's nothing there and it's discontinuous. So I can say a couple different things. If the question asks you where is it continuous, I can say that it's continuous starting and including negative 3/5, that's why I have the bracket instead of a parenthesis, and then anything that's bigger than that. So negative 3/5 to infinity. Or if the question asks you where is it discontinuous, I can say that it's discontinuous on the interval from negative infinity until I hit negative 3/5, because anything over to the left side, there's going to be nothing there on my graph. So it's discontinuous on the interval from negative infinity to negative 3/5. So making sure you're comfortable with answering the question all different types of ways, whether they ask you for continuity or where is it discontinuous.